Okay, we're going to start here with the back of our note sheet, 20B, instantaneous rates of change. So in 20A, we looked at average rates of change over a time period, but it's nice to know if we could figure out the exact rate of change at a certain moment. So for instance, you're going on a drive, you're driving from here to St. Louis, and we want to know exactly how fast you were going after an hour and a half. So you're traveling along, and at an hour and a half, how fast are you going? Right then, like if you look at your speedometer, exactly at an hour and a half, how fast are you going? So we're not wanting to know your average rate of change for the entire trip. We're not wanting to know your average rate of change between miles or hours 1 and 2. We want to know exactly at hour 1.5, how fast are you going? And this is the idea of an instantaneous rate of change. This is the speed of an object at a specific time. So at precisely a certain time, how fast are you going? So if we look at this picture, we're looking at each of these points and trying to understand the instant rate of change at that point. So if we look at point A, if you imagine this as driving or something, I don't know, it'd be kind of weird if it was driving. We don't have any units, so we'll just have to imagine it as something here. So you're traveling along. At this point at A, our line is increasing. When we talk instantaneous rate of change, we're looking at the slope of the tangent line. So tangent line is a word that you learned in geometry. Here's the definition of it. In geometry, you looked at tangent lines to circles. It was a line that intersects the circle at exactly one point, only one point. And so our tangent line here is the same idea. So if we look at A, our tangent line, let me use a pencil and I'll show you lots of not tangent lines. So a not tangent line would go like this. That's not tangent. If we look at, right, if I tried to draw a line like this, that's not tangent. Okay? Those are going through the line. A tangent line kind of skirts the edge and intersects it at a single point. So it's going to look like this. It kind of brushes the edge and touches just at A. This is our idea of a tangent line. Okay? Just brushing the edge of it. And so at point A, we would say positive slope. So at point A, it's going up. If we think about this as maybe a ball that's been thrown in the air, you threw it up, it's accelerating up, it's moving up. Then it gets to B, and this is where the ball turns around and comes back down. Right at point B, where it's at the very, very top, this is like the point where the ball stalls out. So you threw a ball up in the air, and it stalls out for a second, right before it turns around and comes back down. At point B, our tangent line is going to be perfectly horizontal. So it brushes the edge just at one point. In order to do that, it's going to have to be perfectly horizontal. It has a rate of change of 0, has no rate of change. That stalled out point where it turns around and then decides to come back down, that's that point where it has no, it's not increasing, it's not decreasing, it's paused for just a split second. So at point B, it would be 0. Then the ball starts to come back down. So now the ball is moving in a negative direction and accelerating towards the ground. And so at point C, the tangent line would have a negative slope. We're going to look in a minute ways to find these slopes specifically, but right now we're just looking at what would they look like. At point D, the ball is still traveling down. So it hasn't started going back up yet, it's still going down. So at D, we still have a negative slope for our tangent line. Negative for instantaneous rate of change. It's going down. Point E is another moment where it stalls out before it goes back up. So this would have a slope of 0. And point F would be positive. Once again, we're looking at these tangent lines, these lines that intersect just brush the edge and just cross at one point. The entire line, the entire tangent line stays on that side. So it doesn't cross the line, it doesn't cross over, it just touches it at one point. Okay, these are tangent lines. And the slope of the tangent line is the instant change at that point. So let's look at this question here. We've got find the instantaneous rate of change at 2. We're going to do some other stuff before we get there, but we've got this point at 2 is the point 2, 20. They want us to find the average rate of change between 2 and 4. So 2 is there, 4 is here, and we want the average. So this is what we did in 20A. The average rate of change appears to be positive. We've got a positive slope. It's increasing between these 2 points. Whatever we get, we should expect to be positive. So I'm going to do my slope, y2 minus y1 over x2 minus x1. So, oh, I'm sorry, I put 20 up there, and I meant to put 80. So we'll do 80 minus 20 on top, 4 minus 2 on the bottom. So we get 60 over 2, which is 30. We don't have any units here. Why don't we add some? We'll call this time in hours, and we'll call this distance in kilometers. So this 30 would represent the units for the top is my y's, so that is kilometers. The units on the bottom is x, so that's hours. So our 30 represents kilometers per hour. So between 2 and 4 hours, you traveled 30 kilometers per hour on average. Notice you traveled slower here and then sped up. All right, we're increasing here. But on average, 30 kilometers per hour was the rate of change. Question 2 is going to restrict this a little bit more. We're going to go between 2 and 3. The point at 3 hours is at 45. So we're going to find the slope of this line. We're trying to get closer and closer and closer to our point 2. So we're going to find the slope between the 3 and the 2 point. So my y's are 45 minus 20, y and y, over 3 minus 2. So the average rate of change between 2 and 3 hours was 25 over 1, which is 25 kilometers per hour. Same unit as above. Okay, so between here and here, it's 25 kilometers per hour. We excluded this piece where it was faster, so it made it a little bit smaller. We can keep getting closer and closer to the instantaneous rate of change by choosing points that are very, very, very close to 2. So how about we choose this point, 2.1. Now, 2.1, I don't know on my graph exactly the y value. You can't pick that out from that graph, but it gave me this equation. So when t is 2.1, our distance, we plug that into the formula, and that's going to tell us the value of the function at that point. So 22.05. This is the average rate, this is this value right here, 22.05. So when x is 2.1, 22.05. So now we're looking for the slope of the line between those 2 points, the slope of the straight line between those 2 points. So we do the same thing. We do our y's, 22.05 minus 20 over 2.1 minus 2. So 22.05 minus 20 is 2.05 divided by 0.1 is 20.5 kilometers per hour. So between 2 hours and 2.1 hours, you are traveling 20.5 kilometers per hour. We can get closer and closer and closer to the instantaneous rate of change at that point by doing this method. You could pick something even closer, 2.01, and do the same thing, and you can get very, 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 very close to our instantaneous rate of change at that point. I'm going to show you another method. How about the calculator method? So for our calculator method, I'm going to type in the function. So I'm going to type in my y equals, my function is 5, it's t, but we'll use x squared. Here's the graph. If you want to, if you'd like to see the graph like this, you can press Window. My x's go from 0 to 5. My y's go from 0 to 100. And maybe scale every 10. This is scaled every 5, so we could do the same thing, 5. This would, I got a stat plot on, I should turn off. This gives us a graph that's a little more similar to the one that's on our paper. So there it is. If we want to find the instantaneous rate of change in our calculator, we can press second, calculate. Now it's not just going to say instantaneous rate of change. There's another word for it, and we'll talk more about this in C and D, 20 C and D. So number 6 says this is called dy over dx. Number 6, dy dx. This will give you the instantaneous rate of change at any point along your line. So I want to know when x equals 2. Now if I scroll, sometimes 2 will pop right up. There's 1.96 and 2.02. It doesn't pop right up, so that's kind of irritating. But if you just click the number 2, this pops up, x equals 2, enter, and it tells us the instantaneous rate of change at that point is 20. So I'll write down our steps here. We graphed y equals 5x squared. We pressed second calculate. So that's second trace. We've gone there a bunch this year. Number 6. Then we clicked 2 and enter. And that told us dy dx equals 20. I'm going to show you the algebraic method for this, but you will never have to, IB doesn't care for you to actually do the algebraic method, but it does help you understand a little bit where this is coming from. So once again, you don't have to be able to regurgitate this, for instance, but it gives you an idea of why this is true. Why is this happening? So if I focus on, I'm going to kind of sketch my curve down here. I have the point 220. And I want to pick a point just past it, just a hair past it. I'm not picking a specific point. We want a point that is 2 plus h. Maybe h is, I don't know, it's very small. H is very small, just a little ways away. Just like we did here with the 2.1, in order to find the y value, we had to plug in the x value. So this would be 5 times 2 plus h squared is our y value. So we take this, plug it into our function, and that would give us our output. Now I'm going to find the slope between these points. We're going to have some h's involved, but that's going to be okay. So I'm going to find the slope. I'm going to do my y's first. 5 times 2 plus h squared, that's this y. My other y is 20, this one. And on the bottom, I subtract the x values, 2 plus h and then 2. We're going to do a bunch of simplifying. The first thing that happens on the bottom is we have 2 minus 2, so all we're left with on the bottom is h. That should always happen. On the top, I'm going to distribute that out. So 5 times 2 plus h times 2 plus h minus 20. I'm going to do all the distributing. I'm going to kind of skip a step just because we were pretty good at distributing now. 2 times 2 is 4. My middle terms would be 2h and 2h, so that would be 4h plus h squared. Did a little foiling there, a little distributing, minus 20. On the top, I'm going to distribute the 5 through. So we get 20 plus 20h plus 5h squared minus 20. So I distributed the 5 into the parentheses. On the top, we get the 20 minus 20 cancels. And we're left with 20h plus 5h squared all over h. Since h is a factor of both of the tops, we can cancel the h's, and there will be 1 left there. So we end up with 20 plus 5h as our slope between these 2 points. Now, whenever we designed this, we said h is very, very small. H is not 0. 0 would put it like right on top of that point. That doesn't make sense. It's just like littlest, smallest, little bit away. So what we do here is we say h approaches 0. So as h gets really, 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 really little, this approaches 20. And that's the algebraic method. You'll see the book use that method. You will not have to redo that method on your IB exam. Calculator method is fine. Let's look at one more example of this. It says, given the graph of y equals negative 1/2 x squared plus 5 at right, find the instantaneous rate of change at point 3. So point x equals 3 is there. Then draw in the tangent line. Okay, so we want to, I'm just going to use the calculator method. If you would like, if you're curious more about the algebraic method, feel free to ask me during class, and I'll go through it with you. But let's practice our calculator method. So I'm going to start by going to my y equals, and I'm going to input negative 1/2 x squared plus 5. I like to make observations as I'm solving problems. I don't like to just go in blindly. So if I think about the tangent line at that point, I would expect it to have a negative slope. And I know that's not a great line. Oh well, it's a little curvy. But I should expect, right, this is increasing, it's getting bigger. Here it's decreasing, it's getting smaller. So I should expect it to be negative. But we'll see what happens. So we're going to go and input that into our y equals. I'm going to fix my zoom from our last question. So y equals, clear out that, negative 1/2 x squared plus 5. Graph it. Once again, if you'd like it to look more like this, you can practice changing your window. X goes from negative 5 to 5. Y goes from negative 6 to 6. And now we can get a little bit more accurate picture based on what we're looking at on our paper. But you can look at it the other way as well. I need to find the slope of the tangent line at x equals 3. I want the instantaneous rate of change. So we're going to press second, calculate, number 6, which is dy over dx. Second, calculate, number 6. This is where you can trace it, and you can to find your point. But once again, you can't get super close to it, so you can get kind of pretty close. But if you press 3, then enter, it'll give you very specifically. So then we press 3, and it tells us dy over dx equals negative 3. So this is the instantaneous rate of change, which is the same thing as the slope of the tangent line. So this is that. So if a line has a slope of negative 3, that means it rises negative 3, runs 1. So if I try to draw in my tangent line on my graph, I know this point is on it. That's the point it intersects at. So I'm going to kind of eyeball it a little bit, but I'm going to go down 1, 2, 3 over 1. I can also, I can do it again, down 1, 2, 3 over 1. I can also go up 1, 2, 3 and back 1. 1, 2, 3. It puts me off my graph a little bit. That's okay. And this is the tangent line at that point. So it has a slope of negative 3. It intersects just at that one single point. It does have a negative slope, telling us that it is decreasing at that point. So at the bottom, I just made a note. We will elaborate on this. We're going to look at some more algebraic methods in C and D. If you want to watch the C and D notes and then use the shortcut that we learned there, that's fine. If you'd like to use the calculator method, that's fine. The book is going to be using the long algebraic method, like we did on this example here. Okay? So don't feel overwhelmed by this. Feel free to practice it if you like, or ignore it if you don't, and learn the calculator method is completely fine. Thank you for watching. I hope to get C and D uploaded today as well, so you guys have some work to get started on. Your homework assignments for 20A and B is posted, so please get to work on that and ask me for help as you need it.